Hello, in this video I'd like to review eigenvalues and eigenvectors. So let's recall that for a square matrix A, lambda is an eigenvalue associated to eigenvector x if and only if A times x equals lambda times x. Couple of points before moving on. On the left-hand side of the equation, this is a matrix multiplication because we have matrix A times a vector x. And on the right-hand side, note that this is a scalar multiplication. Geometrically, what's happening? Well, geometrically, if we have an eigenvector x, so let's draw an eigenvector here. Suppose it looks like that. There's our x. And we apply the transformation encoded by matrix A. In other words, we perform the operation A times x. And that's really a transformation. It's going to transform the coordinates of x in some manner. All right, so we have our eigenvector x. We multiply by matrix A. And if that's really an eigenvector, what ends up happening is that vector x still points in the same direction, but it gets stretched or shrunk by some scalar lambda. So our result looks like lambda times x. Okay, let's take a look at an example. So let's find all eigenvalues and eigenvectors for the matrix A given by 2, -1, -1, and 2. And you may want to pause the video for a moment and try this one yourself. I'll put the solution up here as well. Okay, so the solution, first let's find the eigenvalues. And we recall from a previous video that to find the eigenvalues, we're really looking at the determinant of A minus lambda. So I'll put minus lambda down the diagonal. So A minus lambda, and we're setting that equal to 0. That gives us something called the characteristic polynomial. So let's work this out. The determinant here of this little 2 by 2 would be 2 minus lambda squared minus 1 equals 0. This gives us the characteristic polynomial, or setting it equal to 0. This gives us something called the characteristic equation. And the roots of that characteristic equation give us our eigenvalues. So if we work this out, we get lambda squared minus 4 lambda plus 3 equals 0. And after a bit of factoring or the quadratic formula, we find that lambda equals 3, lambda equals 1. So these are our eigenvalues. Next, for each eigenvalue, we want to find its associated eigenvector. So let's find the eigenvector, or eigenvectors, let's say, because there's infinitely many of them. So find the eigenvectors associated to lambda equals 3, and then we'll rework the problem for lambda equals 1, because there's different eigenvectors associated to each of the eigenvalues. So to find the eigenvectors associated to a particular eigenvalue, we're looking at finding the solution. So we want to find the vectors x such that A times x equals lambda times x. And more specifically, in this case, we're looking at lambda equals 3 because that's the eigenvalue we're working on. Okay, so let's do that. So we're looking for A, which is our matrix 2, -1, -1, 2, times some vector x equals our scalar times vector x. And by a previous video, we said what this really amounts to is this really amounts to looking at 2 minus our eigenvalue down the diagonal. So let's put that in. Times vector x equals 0. And if you're wondering about those steps, how we went from the first equation to the second, I encourage you to go back and review a previous video on that topic. So at this point, we can put this in an augmented matrix, and we get something that looks like -1, -1, -1, -1, homogeneous system with the zeros. After a bit of RREFing, we get down to a matrix in reduced row echelon form. And this tells us that negative x1 equals x2, and that's correct, but it's not very satisfying. We're really looking for those eigenvectors of the form, a first component and a second component. So let's push through this a little bit more. If x2 is some parameter t, then that implies that x1 is going to be negative t. In other words, our eigenvectors look like t times a -1, 1. And these are the eigenvectors associated to eigenvalue lambda equals 3. And notice that there's infinitely many of them. This is actually something called an eigenspace. And you could say it's an eigenspace with a basis -1, 1. It's an eigenspace with dimension 1 because it has one element in the basis. You can see it's a scalar multiple of a vector. Okay, lots of things we can talk about at this point. But what I want to go back to is I want to go back to the geometrical interpretation. So supposedly our eigenvectors associated to lambda equals 3, they lie on this path that looks like, over -1, up 1. Okay, so there's an eigenvector, and there's many of them that lie on that same line through the origin. So after applying matrix A, after applying the transformation A times X, we get out a new set of vectors, and they all look like vectors pointing in the same direction that we were originally pointing in, but they're 3 times as big. So this new vector, AX, looks like 3 times our original vector x, just a scalar multiple, 3 times as big as what we started with. Okay, let's go and find the second set of eigenvalues. So our next task was to find all eigenvectors associated to eigenvalue 1. And same sort of calculations here. So we're looking at A, which is our matrix 2, -1, -1, 2. Subtract lambda off the diagonal. Times x1, x2 equals 0, 0. So I've kind of skipped a step by speeding up our calculations in here. Putting this in the form of an augmented matrix, we get 1, -1, -1, 1, zeros, and a bit of RREFing brings us down to the following matrix. At this point, we conclude that x1 equals x2, and setting x2 equal to a parameter t, we find that our eigenvectors look like t times the vector 1, 1. Okay, so these are the eigenvectors associated to lambda equals 1. Geometrically, what does that look like? Well, if we start with vectors that look like over 1, up 1, so there's our x. We apply the transformation encoded in matrix A. What we get out is we get out a vector that's pointing in the same direction, and it's actually the same size. So A times x equals 1, that's our lambda, times x. In other words, we put in an x and we get out an x. We get out the exact same vector. Those vectors do not shrink or stretch. They maintain their size and they maintain their direction. So nothing that exciting happens, if you want to think of it that way. Now, a bigger question, suppose we were interested in looking at many points. So suppose we have points all over the xy plane. All right, and we know that we've got an eigenvector that sits in this direction, and we've got a different eigenvector that sits in this direction. And we know that when we apply the transformation given by A, we know what happens in each of those respective directions. So this vector that was originally pointing in the direction -1, 1, that's going to get stretched by a factor of 3. And this little purple vector pointing in the direction 1, 1, that doesn't change its length at all. But the question is, what happens to these other points? You know, where do these other points get mapped to? They're going to move. They're going to rotate somehow because they are not lying on our eigenvectors. Well, what's really interesting is you find that after repeated applications of matrix A, they start to coalesce along these directions of the eigenvectors. And to show you that nicely, I'm going to hop over to MATLAB. So we're in MATLAB, and I have a script here. The details of the script are not as exciting as what it does. So let me run the script so we can see what it does. So we're going to start off with some points in the first quadrant, and they are bounded between 0 and 1 and 0 and 1 in the x and y directions respectively. So we have a bunch of little points, 100 points to be exact, and they're all shown on the screen, and they're kind of bumping into each other, which is why it looks like a black dot. All right, so let me move over our screens a little bit so we can see everything happening at the same time. After one application of matrix A, we start to see those black dots are kind of stretching out along that eigenvector associated with lambda equals 3. Repeated applications of matrix A, this transformation encoded by A, and we see them really stretching out along that direction of the dominant eigenvector, and we see that the other eigenvector is maintaining its unit length 1.